share. And I'll have you mute yourself as you come in if you can. I probably need to have this. I muted myself. Shoot. Okay, so welcome everyone to the first ever open Math 126 exam review. I'm not promising I'm going to do these for all the exams. My plan is to do, I'm in a few hours, I'm about to do one for Math 124. But I'm looking for opportunities. I've taught at the University of Washington for 20 years. Many of you know this. Some of you had me as your instructor last term. I've been creating resources over the many years. I have resources for studying and been making videos for studying. And I thought maybe if I did a few of these open review sessions, I did this last summer, but the summer classes are much smaller. I just think it's a way for me to join students and no one's mad at me for once. We can work together and fight against the exam. So it's a positive experience for me. I have taught these courses for 20 years. I've taught about 22,000 students. And I just have a lot of resources. And I think this is an opportunity for me to share them. And hopefully it's a positive for everyone, provided I can find the time to do it. I am teaching Math 112 this term. So those students are probably going to be mad at me that I'm not helping them right now. Okay, so my intentions here is to do a tour of materials. I think there's still some, and it is snowing here right now. I'm worried my power will flicker off or something. So let's tour the materials first. If something goes wrong, then you will still have stuff to look at. And then I'm going to ask you some questions about what you want to discuss. Sorry, I should have set it to mute everyone when they're coming in. That's my faux pas. But try to mute yourself if you can. So all I want to do here, and you can start thinking about what your questions are, but first what I'd like to do is show you some of my things. And if at any point you can't hear something or something's not working, let me know. But the main page is this. If you do a Google search for Andy Lovelace, you will come to this page right here. And I want you to share this with your classmates. This has been up here for years. I started making this when I started working here in 2005. At the time, students really liked review sheets. Times have changed, but if you click here, you will see review sheets. Some popular ones are like a fact sheet. If you were studying for exam one, you're like, oh, did I get all the vector facts? Do I remember lines and planes? So there's a one-stop shop for your facts, for those of you making note sheets and things like that. And I can't speak to what your instructor particularly is going to ask on their test. I'm going to talk about generally what's on exam one. You can ask me specific questions in a little bit, but that's there. Particular things that I'm proud of are this 12-5 practice sheet where you can practice finding lines and planes, and I have solutions with it. I have a video in my YouTube. Okay. So with this, I've just in the last year, the last 6 months, I've started making videos here. And today I've been actively building ones for you. And over the next 2 days, I'll add 2 more. I just didn't have time today. And this is just stuff I'm trying to create so I have it in the future. So I made an initial video which says, here's a quick rundown of the exam, and I'm making 5 short videos of vector facts, lines and plane surfaces. I finished those, and I just need to make some on 3D fundamentals. So I'm trying to make short little topics for my students in the future. And I'm partially trying to get feedback on what works well. I don't really have endorsement from the department. They're not mad at me for doing this, but I'm doing this on my own. I'm just seeing what would be helpful so that we all can feel better about these courses. Okay, so that's the plan. Anyways, so that's there. If you go to Dr. Lovelace Teaches Math, I also have a bunch of stuff that I personally want to share that I just think is fun and funny. So that's my one selfish, I want a bigger audience. But the playlist here is don't go to sports and math, or you're going to see a fat guy serving a tennis ball. But look at, and the fat guy's me. I wasn't insulting anyone but myself. Here's Math 126 prep. And here's Math 126 supplemental videos. Unfortunately, my Math 126 videos were made some during the pandemic, so they're not quite as polished. They don't have timestamps in all of them, but they're still all right. Yeah, all right. Thanks for the nice thoughts. But mostly, I'm also thinking about this is a great time for me to thank all these students that have supported me. Anyways, let's go here. So, so you've seen the review materials. Just do a Google search, Andy Lovelace. There's a link to the YouTube channel. That's it. Now, as I think about Math 126, which I've taught a lot, and I'm teaching in the spring and I'm teaching in the summer, and so this also has the benefit of really trying to polish my materials for the years to come. Exam 1 is typically these topics. This is kind of 12.1 to 12.4. This is 12.5, lines and planes, and that's usually a big one because it's the section where you have to think the most through a problem, I think, of this first group of stuff. 12.6, and then I'm kind of clumping 13.1 and 13.2 together, and 13.3 and 13.4. Is your exam going to include 13.4? First question for the chat. Do you know? Okay, good. Sometimes 13.4 is on the first exam, sometimes it's not. It isn't a lot to add, so it's not something to fear. 13.4 is kind of the fun section, but we never have very much time to give it its due course. So what would we, so from here on out, you know that I knew I wouldn't be able to cover very much. That's why this morning I started making these extra videos where I went topic by topic. But I'm kind of curious either which topic you would like to see the most, or which of these I have my two most recent exams. Actually, Spring 24 is not in my archive, so this is a fresh one. Lines and planes, absolutely. Love it. Okay, so we have 12.5 and 12.6 have you pulling your hair out. Lines and planes, intersections of lines and planes. I'm just kind of collecting a few thoughts.
Oh, there you go.
And we'll try to, that worked. So by 6:10, we'll be hitting some problems. I hear 13.1 and 13.2 a little bit. Intersection of planes I saw. I'm just trying to note things as I see them. Parametric, okay, that's hitting on here. Okay, we're going to see all those things in a second. If you really want to be good with lines and planes, you should do my practice sheet and watch my video that goes with it. I think I got it nailed. But yeah, distance between parallel planes. Okay, that's a specific formula. I wonder if that's in my review sheet. Yeah, 12.5 and 12.6. I do like that. So let's hit 12.5 to start with. All right. And we'll kind of bounce back and forth and see if we've hit these topics. I'm just going to pick one of my old exams that's not in my archive, and we'll see how this goes. And I'll ask for people to hit me up. So this is one of my old exams. Surfaces are messing with me. All right. We can take care of that. We'll take care of that before the day is done here. So as I look at old exams, I always like to tour them. If I was a student, I'd constantly be opening the exam archive. This doesn't sound like fun, but I'd constantly be opening the exam archive like before class and looking at it for 3 minutes. It's a very useful thing to be doing. So anyways, I would say, uh-oh, I got to find a coordinate. Looks like a projection. Area of a parallelogram. Okay, that's a cross product. And I would kind of be testing myself. Which one of these would I know how to start? And if you did a little bit of that each week, you're going to do better on the test. Okay, let's see what this one looks like. Here's a question none of you have seen before. Maybe I have a video somewhere about my spring 2024 exam, so maybe you've seen it. I think this has to do with something. Consider the line given by this. Consider a second line. It intersects this plane at the z-intercept. Give parametric equations for the line and find the intersection of the two lines. So that's a line question. Let's try to extract as much juice from this as we can. There's a lot going on there. I don't know what's wrong with the person who wrote this. Oh, it was me. Okay, so let's try this. What this question says, consider the first line. I'm sorry, it's probably a little blurry, but I'll write it down here. So I have two lines. One line is given by 9 plus t. So this is good. We'll take care of lines. Z equals. Maybe I can take the video and turn it into a Panopto video and then share that. Let me think about that after. But somebody's asked me that before. We have this second line, and we don't know what it is. The moment you see the word find a line, you know that you're searching for 6 numbers. Oops, I'm not following. Well, I'll continue to not follow my own advice. for a second. And let's talk about a few things here. So when you look at this line, the most important numbers are the 1, 2, and the -5 because they form a vector. So when you look at the equation line, that's like the equivalent of slope. Why do we do it in a vector? Well, because we have three things. So you can't just take the fraction of two of them. In 2D, you divide these two things and you call it slope. In 3D, you can't do that because you have three things. So this is like the generalization of slope. If x goes up 1, y goes up 2, z goes down 5. That's what we're talking about when we're talking about a line. And unfortunately, we use a parameter because there's no other nice way around it. In 2D, you didn't have to do that because you could just turn it into a slope. So that's one of the biggest changes in 3D. This 9, 4, 1 is where we're starting. That's like where you are at time 0. You can see it when you plug in 0. Okay, so we call this a direction vector. So the moment someone says find a line, several things happen. I like to draw, I don't know if this is helpful, but I always draw a line. I always draw the exact same picture. I put a little dot here, and I put a little arrow here. And then in my head, I think, what do I want? So if you've watched my videos, you know the answer to this. The moment you write down the equation of a line, what are the two things you want? Somebody tell me in the chat.
A dot and a direction vector.
A point and a vector, absolutely. So we need a point on the line, and we need a vector parallel to the line. And then the next question you ask yourself, I sort of have this belief that all of math boils down to, or most problem solving boils down to figuring out what you're given and what you want, which in real life are hard questions to answer, but in math are a little bit easier. Okay, what am I given? I'm given that you have this second line and it is perpendicular to this plane. So this has turned out to be a good question in that I'll get to cover a bunch of stuff. So now let's talk about planes for a second. I've got this plane. I'm just going to draw it here for a moment because I'm not very good at drawing them. And we've got an arrow sticking out of it, and we've got a dot on it. And for planes, you have a point in a direction, a point in a normal, excuse me. So what is the normal vector for this plane? It's a lot of information to dissect in this question. That's the challenge. And that's why I like to draw some of these pictures. So the normal vector would be 3, -1, 5. It's these numbers, 3, -1, 5. So hopefully you're getting in the habit of the very first things you see when you look at a line are the direction vector, 1, 2, -5. And when you look at a plane, these coefficients are the normal vector. Those are the things you've been doing. Now, if you watch my video, I say that there are 3 situations I absolutely love. And the 3 situations I love are when you have 2 lines that are parallel, 2 planes that are parallel. And the reason does anybody know why I like those? I love it when a problem says you have this other line that's parallel to a given line. You have this other plane that's parallel to a given plane. I call those the happy situations. In those situations, you can use the same vector for both. So 2 lines that are parallel, we love. 2 planes that are parallel, we love. And when there's a line in a plane, we really like it, not when they're parallel, but when they're perpendicular. So imagine I take this line, I'm going to redraw my purple line. I'm going to draw it perpendicular. Why perpendicular? Because it said that. We love this situation. This is the third happy situation. Why is that a happy situation? Well, because what am I searching for again? A point and a direction. I want a vector that points this way. Do I have a vector that points that way? Absolutely. So this is something not everyone emphasizes, but in recent years I've realized I need to tell students that if it's 2 lines that are parallel or 2 planes that are parallel or a line and a plane that are perpendicular, those 3 situations mean it's going to be a nice problem because they're already giving you a vector that points the way you want, meaning I can use the vector 3, -1, 5 as a direction vector for the line. To me, it's easy to remember. Same object, we want it parallel. Opposite object, we want it perpendicular. I don't know how else to say it. Cool. Question on that piece. That was an important, we did a bunch of stuff there, but where in the world am I going to put that 3, -1, 5? on this page? Think to yourself where it goes. Goes right over here. There's no way for you to answer that question. All of you are trying to figure out, how do I type in an answer to what he just said? That's a terrible Zoom question. Okay, so there we go. Those are those three situations. You can raise your hand and unmute. I don't know if somebody raised their hand, if I would see it. I probably should double check that. But let's pause for a second there. So we did a few things. The moment I see line, I do the equation of a line and I start trying to find those two pieces. So what am I missing? I need to find a point. Did it tell me anything about the point? And this is where it's helpful to know what you're searching for, because now I have a very clear goal. I need a point that's on the desired line, somewhere on this desired line. What did they say? Yeah, it intersects the z-intercept. I tend to, I think I do when I teach this, I do a good job of these pieces of, I really want students to know how to use these. If you can just find the equation of a plane but can't use it, that's no good. So if someone gives you the equation of the plane and says, I want the z-intercept, what does z-intercept mean? So we're combining conditions. It's the same thought process in 2D, but 3D really makes you think about it. So if you're on the z-axis, we already know two of the coordinates, 0 and 0. Absolutely, you guys are ahead of me. How did you type that so fast? If this is 0 and this is 0, then z has to be 6. And that's why I sometimes talk about this. If I need to graph something, a plane, I plug those things in. So the point they told you indirectly was 0, 0, 6. So I'm unpacking a lot in this problem, but there you go. So I just wanted to talk through all those things. At this point now, we're going to switch gears to this intersection question. Cool. Question on that before we go to the intersection piece? Do we want to see the intersection piece? Yes, yes, yes. The answer is always yes. Where did the 6 come from? Great question. I did a little arithmetic magic here. So because we're talking about the z-intercept, I plugged in a 0 for x and I plugged in a 0 for y. So I did 3 times 0 minus 0 plus 5z is 30. And then I divided by 5. With me there, Mira? Sorry if I'm saying your name wrong. All right, all right. So let's go. We're going to play the vanishing game here. There's a separate thing that comes up. I mean, this was a great problem. I did not intend it. A great problem for a discussion. That usually doesn't happen. I usually pick a problem and it's terrible for discussion. But anyways, you might say it's not much of a discussion. You're the only one talking. Okay, so the question now is, how do you find the intersection of two parametric equations? The way you're going to do that in this section and in 13.1 and in 13.2 is the same. Okay, so how do we find the intersection of two lines? Now you can have two lines that run into each other, but you don't necessarily there at the same time. I always do these examples of if I'm running this way and my friend is running this way, we're not going to run into each other, but our roads still cross. And so in order to figure out if the paths cross, you have to use a different parameter. And that's where I made a mistake at the beginning, and I allowed myself to make it. I would never have put a T here. I would have put something else, anything else. W, Q, a little broccoli symbol, whatever you want, but I think I'm going to put a U. Now I've removed the idea of assuming we're running at the same times, and I've separated them. That's an important little principle at play. I think I might have had a visual ready for this. I was kind of trying to guess what questions would happen. Oh yeah, I'm on it. So here are two lines similarly, and let's set them both moving at a given time. These are these two people. Ready, let's go. Go. Oh, I have a third one. What's that third person doing? They weren't there at the same time. These two people, these two parametric equations were not there at the same time. So if you just set them equal and start solving, you're not going to get a solution. You need to separate the variables and make it so they're there at different times. Let's put the blue guy there. And then we want the other one to be there. What's this green person doing? Okay, so here we go. And then I move this other one. Can't seem to do it. Anyways, the important thing is when you're working with parametric equations, every time there's a new parametric equation, you should use a different letter unless you're actually witnessing motion that's happening at the same time. So that's the point here of this question. That really doesn't have anything to do with lines and planes. So sorry that snuck in here. So that was it. Now we're going to combine conditions. This is the method for solving anything in this course, which is the take it and shove it method. Substitute. So you're going to do 9 plus t is 3u. We're going to do, and this unfortunately happens a lot in this course, situations where you're solving and there's lots of variables. Negative u, and you're going to get 1 minus 5t is 6 plus 5u. But that's a success because we went from 5 variables to 2. Orthogonal means perpendicular. Just a fancy way to say perpendicular. We use it in this sense because we're talking about lines and planes and lots of different objects. And sometimes the word perpendicular, I think, has a certain connotation. So orthogonal is the catch-all for perpendicular. The angle between them is 90 degrees. Okay, so now we're going to start combining. We need to combine all 3 of these. And the most likely answer is there is no intersection. But let's keep going. So you're going to pick whichever one looks the simplest. In my mind, it's this one. And I would do u, actually, I don't know, but it doesn't matter. I would do u as negative 4 minus 2t. And I'm going to shove it in one of the other ones. So let's shove it into the first one. This is how we do all solving of systems. And now I'm combining 1 and 2. And I get 9 plus t. I feel like I'm spending too long on this question, but we're hitting a lot of important little things. Plus t equals minus 12 minus 6t. 7t equals negative 21. T is negative 3. Sorry, I fly through that. Is there a recording for this? I am recording it. You just have to figure out how I'm going to post it. Once I have that, I can plug this in here and I get u is... Why do we take u instead of t? Doesn't matter. You could have solved for t and shoved it in the other. You could have solved for u and shoved it in the other. Your goal in solving a system is to reduce the number of variables. We went from 5 variables to 2. Hooray. We went from 2 variables to 1. Hooray. That's always the goal. And then once you've solved for one of the variables, then you plug it back in everywhere. And here I'm going to get 2. And then there's something I haven't checked yet. Does anybody see what I haven't checked yet? This unfortunately happens in these because we have too many equations. I have not checked the third equation. Yep. So the last thing we have to do is check the third equation. I know this is a lot, but if you put in a 2 there and a negative 3 here, does it work? If it doesn't work, they don't intersect. If it does work, they do. And we have found the intersection. So let's see, does it work? Probably, because this was an exam question. This is 16. You put a negative 3 and this is 16. So we have found that those 2 lines do intersect. So that was several different things there. And we hit a lot of stuff, but I hope we're picking up a little bit as we go. So did the question ask for the point of intersection? Give parametric slide and find the intersection. So the intersection would be, we can double check now, when t is negative 3. So if we put a negative 3 there, we get 6. 2. Now I'm doubting myself. Negative 2. And I'm putting in a negative 3 here, so it's 16. And as a double check, you could put your u in for 2 over here, 6, negative 2, 16. Hooray. That question had a lot of moving parts, but the key was I needed to find the equation of a line. I was looking for a point in a direction. This one had a lot of stuff to it, but I'm going to move on because I just want to be aware of our time. I can go a little bit past 7, but I do have another review session at 9. Okay, let's look at another one because I think this was already asked. And mostly if I go past something too quickly, that's why I've been making those videos this morning of, okay, you could go listen to this fool talk a little longer on my YouTube channel. Okay, so here we go. Find the equation of a plane. So I always think, if you're new to this, it's normal to feel uncomfortable in 3D. That's why you need a process. So the moment you see those words, a bunch of things automatically happen. You don't need to read on. You should draw this. This is something I've only been saying the last 3 years, but I actually think it's one of my best bits of advice, which is to draw this picture. Now, here it's not going to help us very much, but I find that giving students something to attach their brain to is helpful. So the moment I see that, I do that, and I also do this. X minus plus Y minus plus Z minus equals. And we're looking for a point. And if we can find the point, it goes here. And we're looking for a normal. Normal. A, B, C. And if we can find that, it goes here. So I like to set up all of that structure immediately, because even that exercise of writing those things there to remind you of your goal for the entire problem, and that will be my guiding light through this whole problem. And you know all of that the moment you see find the equation of a plane. And you can see I did that similarly when it says find the equation of a line, I do that. The thing that bothers me is when students are taking the test and this question says find the equation of a plane, and they give the equation of a line. That's a preventable mistake. Okay, so then I start to dig through the information this is what I want. Now I'm going to dig through what was given. You can see I've built up this. I think sometimes people think they have to see a problem and know the whole way to the end, but write down the things that will help you. Okay, that passes to the point 3, 2, 1. So that immediately gives me information. 3, 2, 1. Done. Now I'm down to just 3 numbers. This is going well. And contains the line. Oh, that word. This is the word that has troubled students for 20 years. The word contains. Anyways, the line of intersection of these two planes. Uh-oh, intersection of two planes. That's another little bugaboo of this course. I don't know what bugaboo means, but I'm pretty sure that is one. Okay, so let's get going here. And since this is an open for all Zoom, you're going to get all my bad jokes. I have no filter. All right. Here we go. So let's go. So contains means on. The word contains is not the same as orthogonal. That does not mean perpendicular. If it was orthogonal, we'd be really happy. We like it when a line is orthogonal to something. Contains, we're a little less happy. Okay, and if you missed the beginning, you don't know what I'm talking about there. If you were at the beginning, you still don't know what I'm talking about. But anyways, there's this line. So now we're going to embark on what I think is the right way to think through these problems. So the moment someone asks me to find the equation of a plane, I do everything we just did. And there's a lot of questions you encounter in the homework where everything is given, meaning they told you a normal. Now in this problem, I don't see anything based off of what I just went through that tells me this. So that was not given. So then I have a different thought is, well, okay, so if someone doesn't give me a normal, what's the tool you learned in chapter 12 that finds a normal? What's the tool that will take a plane and find something that points right out of it? It's a cross product. So this is the reason you learned the cross product. One of the main reasons you learned a cross product was this. Now, in order to use the cross product, we are going to need something. So now I'm going to start embarking on trying to do a cross product to find n. Let's reverse engineer it. In order to find n, I'm going to have to do the cross product of two vectors. What can you tell me about those two vectors? They are both going to have to be parallel to the desired plane. It's like we're going to find two lines. Sometimes I don't know if I have a pen handy going off screen here for a second. Sometimes when I'm in class, I often have students ask me, why can't we just use slope? So here's a plane. This is poor planning here. Oh, that piece of paper was my mouse pad. I got a new desk, which is made of glass, and now my mouse doesn't work. So anyways, if I want to describe this plane, I can't just find the slope because there's infinite number of slopes. But if I can find two slopes, not slopes, but vectors, That's enough because once I know two, now if you can see them, I can take their cross product. So the strategy becomes find any two vectors on your plane, and then you're done. So it's kind of surprising that that's the strategy when you first see it, and it's uncomfortable because most people in this class haven't done this before, and you're used to being in classes where you have done a little bit of the things before. So I need two vectors that are parallel to the desired plane. That becomes my goal. And the moment I knew that this wasn't given, I knew that was my goal. Okay. And that's it. Watch my video where I talk through that. It's either given or you're trying to find two vectors parallel to your desired plane. Okay, so now we're going to have to find these two vectors. Now, usually I say, if you can find your way to finding 3 points, then that automatically finishes the problem for you. Why do I say that? Because if somebody gives me 3 points that are on this plane, P, Q, and R, can you see your way to finding two vectors? Yeah, you can do PQ and PR. So your other strategy is, can you find 3 points? And I see a way to find 3 points. That's how I would do this problem. It's not the way most people would do it, because most people like to be clever. I don't like to be clever. I like to just do what is logical to me. Okay, so anyways, I have 1 point. I just need 2 more. So that's my thought process. When I see this problem, I go, they didn't give me the normal, so I'd like 3 points. Can I find 2 other points that are on this plane? So now I'm going to read the rest of this. It contains the line of intersection of those 2 planes. Now, if we're talking about the line of intersection of 2 planes, how many points are on the line of intersection of 2 planes? I'll show you in a second. Here's the line. I knew people would ask about this. There's the line of intersection of 2 planes. How many points are on there? It's more than 3. There's an infinite number of points on there. I don't need all those points. I just need 2. So this is my belief, is that if you're doing any problem that has the intersection of 2 planes, find 2 points and that's it. For some reason, textbooks always want to take the cross product of the normals to find a vector that points in that direction, which actually is true and is clever, but it's not faster. So this is my own opinion that I never do that. You'll never see me take the cross product of those 2 vectors unless someone forced me to. In class, I teach both methods. But anyways, here's what I do. I go, I have 2 planes. And that's my opinion. It's not wrong to do it the way the book does it. This is just one place where I differ. Because in my mind, if I can find 2 points, I will be able to finish the problem. And I just need 2 points that are on these, and I'm good at algebra. Maybe that's the other reason to not do that. If you don't like algebra, then maybe this method's no good. Okay, let's move this over. Ah, no. Forget it. We got to fit it. So if we were really good, we could just guess numbers that work, but I'm not that good. So I'm trying to find numbers that work in here. So what we try to do is we reduce it. We reduce it to 2 variables, then it's much easier to guess. In this case, I can see an easy way to combine these. I would add them side by side. You can also solve for y and substitute in, but I'm going to combine these. It's the same strategy we were doing with lines. Combine your conditions to reduce the number of variables. I'm on a mission to make sure everyone knows that. Is that something that's been around for as long as you've been finding intersections in your math class? I find people sometimes still don't know this. So I added the equations side by side, which got rid of a y. And then I'm going to simplify. I'm going to divide everything by 3. And now, the goal here is to find 2 points that do that. So can you find me any numbers whatsoever where the first number plus 2 times the second number is 4? Give me an example in the chat. X equals what and Z equals what? We're going to find a whole bunch. Yep, 2 and 1 works. 4 and 0, yeah, that's what popped into my head. Any other ones? Students don't like choice, so I understand this. But yes, 4, 0 works. You could do 2, 1. You could do, these are X and Z. You could do, what were the other ones? 0 and 2. All of those are good. You might notice that I'm missing something though. So let's do 4, 0 and 0, 2. What am I missing? I'm missing the y. And often students tell me, where do I plug it in? And the answer is always you plug it in everywhere. Because what you're trying to do is find something that works in both. Yep. So if you plug in a 4 here and a 0 here, you see that y has to be -3. And you should double check. If you put in a 4 here and if this was a test, I would double check. Do I get a -3? No. So I did something wrong. Absolutely. That's why I check. I wish that would have been on purpose and not by accident. Y should be 1. It's just bad arithmetic. And 1 is there. That's why I check. I proved it. Okay, and then the next one, if I plug in a 0 and a 2, 0 and a 2, I get -1. Don't trust me. -1? Geez, did I do it wrong again? Why is -1? Oh, shoot. Y is -1. But if I put a -1 here, oh yeah, that's fine. -1 plus 10 is 9, you fool. Okay, so there we go. Now I have 3 points. And how do we finish? And we just did 2 tough problems, but I hope I've at least given you a few ideas. How do we finish? We need these 3 things. So you need to sort of compartmentalize your thinking and say, the moment someone hands me 3 points on a plane, I know what to do. Yep. So you're going to do, and let's organize it. We're going to do PQ, and this is worth our while. I apologize that this is taking a while, but we know this is coming on the test. Lines and planes always appear. And again, you can watch my other videos for more details, but I'm going to do some subtraction. 4 minus 3, 1 minus 2. So I'm going to get 1, 1 minus 2. This is one of the places that's most likely for there to be an error. You can always do a double check in the following way. Add those numbers to P and you should get Q. Add 1, you get 4. Add -1, you get 1. Okay, so that's our double check. That's how we think of vectors. Now let's do this subtraction. -3, -3, 1. This minus this is -3. This is -3. This is 1. Doesn't matter which vectors you choose. It turns out that if you, actually in this case, the length will be the same. It's just a question of which way it will point. And that's that right-hand rule. But I better not start that because once people start asking me about the right-hand rule, it takes like 5 hours of discussion for something that doesn't even matter for the course. So yeah, it either points up or down. Okay, so let's do the cross product. Could you please explain the cross product of the normal vectors method, please? Yes, I can in a second, but let's finish this problem. So here's what I do next, is I do I, J, K. Your instructor might write this differently, but based off, I've taught the courses that follow this, and I think it's good for us to get in the practice of computing cross products this way. And then you only have to do little bits of arithmetic. You cover up the first column, and here's what you get. These two together is -1. Those two together is 3. Then you cover up this next column. 1 times 1 is 1, 3. Then you cover up the last column, -3 and 3. And I don't trust myself. I'm always like, I probably made a mistake. So I check it. And the whole point of a cross product is it's perpendicular to previous two. Checking takes almost no time. You just multiply this times this, this times this times this is at 0. -4, -2 plus 6. And I find it satisfying to check. So not only do I want to check, it feels good. Okay, then I get 12 minus 6 is 0. Aha, now I know my answer's right. So especially in Math 126, it's very important you build in this checking. 2, -6, and we're done. So we did a lot of things there. I showed you how I think you should do cross products and never do them wrong, how to approach a plane question. You know, that's stuff I teach over many days, so I know there's probably unanswered questions, but that's why you can watch my other videos. Questions on this piece before I talk about what's being asked? Okay, so first, Nia asked, what if you do the other method? You do the method of the cross product of the normals. If you do the method of the cross product of the normals, here's what happens. In this problem, it's particularly undesirable to do that, but I'll explain in a second. It's this clever idea. It's not, like I said, it's not bad. It just, for me, most of the time, it's not any faster. And logically, I like the other way of thinking about it. But if you have two planes that intersect, it's this basic idea of this normal vector has to be perpendicular to the vector on the line because the vector on the line is on that plane. Similarly, this normal vector has to be perpendicular to the vector on the line, which means the vector that's on that line must be perpendicular to both, which means that if you do two, so it's just many steps of logic. That's one thing I don't like about it. But if you do the cross product of those original normal vectors, these two original normals, you're going to get a vector that points in the direction of the intersection. Now, the problem here is that's not what we want. That would just give me a vector that points in the direction of this line. And so even after you find that, what would you do next? Does anybody know what you'd have to do next? You'd have to find a point on the intersection. And so you'd have to do this anyways, which is funny to me that you would do this method and then have to do my method anyways. So that's why I was like, if you have to find a point anyways, it's not that much more effort to find a second point. That's my opinion. Okay, that's the point on that. So the other question was, does the cross product of two vectors of intersecting planes always, it's always on in the direction of the line? If we have 3 points and we want to find a plane between them, after we find the cross product of the two vectors between them, can we use any of the 3 points? Yes. Yes, yes, yes. Does the 3-point method always work? You know, sometimes you could be given a problem where it's unnatural to find 3 points. Well, let me break out for a second, and hopefully we can move on to another topic. But if I gave a question here, where you had a plane, and let's see if I can construct an example. I told you it goes through the point 1, 2, 3. Let's call that P, and it goes through the point, I don't know, 0, 0, 5. This is not an accurate picture. And I told you there's a vector up here, and this vector is, this might not be reasonable, but let's just say it's 1, 3, 6, and that this is parallel to the desired plane. And I said, find the plane. There is an example where it's impossible to find 3 points directly from what they gave you. So the answer to the question is, does the 3-point method always work? No. The vast majority of the time, you can find 3 points. But in this question, it doesn't work, but it's because it's easier. The goal is not really to find 3 points. The purpose is to find what? Did anybody catch what the purpose was? The real goal is not to find 3
Two
points, it's to
vectors.
find the thing that follows from that. To find the 2 vectors parallel to your desired plane. So if they're already giving you 1 vector parallel to your desired plane, you just need to find PQ, whatever that is, and then do the cross product. So anyways, just to this end, to sort of highlight something I'm saying here, 12.5 flowcharts, visuals, and derivation. Is that what I wanted? No. I might not be able to. Oh, flowcharts. These are the world's worst flowcharts. I don't know why I call them flowcharts. But anyways, this is it. This is what I'm talking about. The process of thinking. To find the equation of a line, you need a direction and a position. If the information is given, you're done, but you have to recognize it's given. And that's true in both cases. For a line, you're trying to find 2 points because then you can subtract and get the direction. For a plane, you're trying to find 3 points, but really the goal is to find these 2 vectors and do their cross product. Since there's enough going on, it's really nice to have this plan of attack. There are some special cases, the intersection of 2 lines and the intersection of 2 planes, but luckily we've already dealt with those a little bit here. What's the difference between a normal vector and a direction vector? A normal vector, the word normal means perpendicular. A normal vector is perpendicular to a given plane. So one thing to add to this, if I could remake this, you're seeing me snip as we go here. So maybe next quarter I'll do this, but let's go back here. I know that took a while, but it's valuable stuff we just did, so I apologize if we didn't hit everything, um, but the price is right. This is a free review session. Okay, so this is why I add the following things. In my mind, there's this picture, and I always draw the same picture. This is the direction vector A, B, C. It is parallel to the desired line, and we have a point on there. And for this one, the picture in my mind, it's always the same picture. I don't try to draw it accurately, is this. The normal vector is perpendicular to the desired plane, and we have this point x0, y0, z0. That's what we're after. So the problems start with that. I start every single problem with drawing this picture or this picture. This picture in particular is very useful because it gives you a place to take the information and draw it. And that is really valuable, I think. Does that answer your question, Lily? Sort of. Could you subtract the plane equations from each other to eliminate a variable? Yes. But the goal is always to reduce the number of variables. Okay, the other questions, I feel like we somehow danced around. Oh, there was some 12-6 questions and there were chapter 13 questions. Do we want to move on to 13? I feel like maybe we should. Does anyone have a particular question from these exams? And we'll go over the time a little bit. I had planned that. Sue Fall, thank you for a particular question. Fall 2023. Oh, darn, I don't have it. Question 3. We're going to do a little dive here. How complicated the interval is usually not complicated at all. I think I had to by parts once on a part of a question. There's just not that much integration yet. Don't worry, it's coming in chapter 15. Okay, this is question 3. And I obviously don't know. I was trying to kind of confine myself mostly to my question, but I think I know these instructors. I don't think they'll get mad at me for doing a few of their problems. Ooh, a space curve. Something about the word space curve. I don't use that very often, but it means a 3D curve. Makes it sound like something more is going on. Okay, so we need a blank space. That sounds like a Taylor Swift song. Okay, here we go. Okay, so here's a question that I think hits on, then you find the direction vector. If you take the cross product of two planes, by that I think you mean the cross product of the normals of two planes. That will give you a direction vector for the line, but you're still going to need a point. And that's the problem. I always feel like if I'm going to find one point of intersection, why not find two? It takes like 3 seconds longer. Again, that's my own thinking, but you don't, most people will do the cross product and then find one point of intersection. I'm like, let's just find 2 points of intersection and be done with it, not do a cross product. Okay, so here we have a space curve. A space curve just means this. It's a parametric equation. But instead of it being a line, there's a more complicated relationship in how things behave. Now, as you get more and more into this, you'll realize that if there are sines and cosines, it's some sort of circular motion problem. And maybe if I have time, I really want to make a 3D picture of that. But it would take a moment for me to do. I might be able to do it quickly. But anyways, find the equation of a quadric surface. This is an important strategic thing. Like if I wanted to visualize this, I could plot points all day. For example, if I plug in 0, let's see what x, y, and z are. We get 0, we get 2, we get 0. And I could keep plotting points and trying to connect them, but it's going to be hard to visualize. It would be really nice to know some relationship I can make about them. So this is a particular strategy called eliminating the parameter. And the main two tools are to solve for t and substitute. That's one of our strategies. And unfortunately, that's not going to work in these two because I don't know how to solve for t. You could solve for t here. I mean, you could say y minus 2 is t squared. But since the other two are messy, I'm going to hold off for a second. The other strategy is we love to have circular motion problems. Circular motion problems involve things that have sine and cosine. And you have this one principle at play. This is the one identity I tell students you have to memorize. If you only have room in your brain for one trig identity, it's this one, which is that this squared plus this squared is always what? I haven't been asking you very many questions in the chat. It's always one.
One.
That's always true. Yeah, thank you. Thank you, Mimi. Those are familiar faces. Obviously, three. Also correct. Um, so in this case, I have a sine here and a cosine. So this takes a little bit of work to realize this. You'd only do this if you saw there were sines and cosines in the problem, but they're not by themselves. And so what you do is you get them by yourself themselves, which looks funny when you see it. Oh, there's somebody still answering. This is the bad part about chat when we were doing back in the um, Zoom session days. It's too distracting, but we can handle it. Okay, so what you do is you say, I don't know what t is, but I know that this squared plus this squared has to always be 1. So x squared over 4t squared. What I did is just squared that. That's actually sine, but maybe it'll let me get away with changing the order. Z squared over t squared is 1. And unfortunately, there's still a t there. So I really would like to multiply both sides by t. Honestly, I would have liked to multiply both sides by 4, but I've already written this, so let's stop right here for a moment. So I'm still, unfortunately, made some progress. I've been able to combine x and z. And now I'd like to get rid of that t squared. Is there any way I can get rid of t squared so that I only have x, y's, and z's? And there's no promise that this is going to lead anywhere, except for the fact that the question says it will. In general, you don't lead to a nice surface, but this one does. T squared is y minus 2. That's it. So this is valuable because if you knew what this 3D surface was, every point on the curve will be on that surface. But the real question was name this shape. So here's my chance to tell you how to remember the name of the shape without having to look at a table or put it on your note sheet, if we think that would be valuable to us. Here's all we do. Oh, I can't use my thumb. Darn it. I usually call this the thumb method. If I can't use my thumb on the computer screen, you can't see it. So here's what we're going to do. We're going to cover up X. And if I cover up X, I'm going to get this. I would like you to tell me if you were to graph that, what would happen? So imagine you put your thumb over X squared. It's a parabola. That's it. So if you cover up X, we're not actually covering it up. We're replacing it with a constant. But one of the traces, we would say, are parabolas. Now let's play the game again. Let's cover up Z. 1/4 x squared equals y minus 2. What is that?
A parabola.
Thank you, Mimi. Parabola. And we're down to the last one. Now, the moment two of the traces are parabolas, there's a name for that. This is how I remember the names. This is why I don't have to look anything up. If it's a paraboloid. That's it. So that makes it easy for me to remember. I don't have to look in a table. Lastly, what happens if you cover this up? Now, you got to be a little careful here. If you call it 0, it's not possible because it's a negative. But if you called it like 10 or 100, it does make sense. So when I cover it up, I'm just thinking about form. So what does it mean if you have x squared and z squared and a constant on the other side?
Is it an ellipse?
It is absolutely an ellipse. It's an ellipse because the 1/4. So somebody said long ago, how should we name this thing? The thing that from two directions looks like a parabola and from the other direction looks like an ellipse. Well, we should add some weird subscript to the word parabola to indicate two, and then we should use this as the adjective. That's the naming convention. So we say it's an ellipse. I never know. Actually, I got to think about this. Is it elliptic or elliptical? Maybe there's an English major in here.
I think
Elliptical.
it's elliptical.
Elliptical paraboloid. Thank you. But this tells me the trace in two directions is a parabola. So you can also do this in a table. If two things are squared and the other is not, it's a paraboloid. It's an elliptical paraboloid. That's valuable because it gives me, okay, let's try this. I don't know what's going to happen. Don't know. Here we go. Oh, we're really going to test how well I learned to graph things during the pandemic. Let's go. Add an object. Let's do, this might not work. How can we find more information on finding the trace curve name in this strategy? Well, watch my videos on 12.6. So what I want to do, come on, gotta be faster than this. Okay, this is x to the second. Let's go faster. Let's go. I got it. Z to the second, and then I need y minus 2, and then I don't want that other one. Why are you there? That's this thing. I want to allow negative. I want to be able to allow more values. Okay, there's my paraboloid. Get out of here, lines. I'm messing up my other example. I don't care. There's my paraboloid. It's a parabola coming out this way. The traces, oh, it's going to take me too long to do that. The curve itself, though, I can show you. Parametric curve. Let's see, it was these ones. I'm going to write it real quick. 2t sine of t. And this is maybe a value just if you're continuing on. This is a free online thing called math3d.org. This is t. It's not necessarily the best tool. It's just the one I know really well. And I'll do one more thing. Here we go. Here. And let's send this thing in motion. So I'm going to t. Yeah, I know. Almost there. A few more seconds, then we'll get back to questions. There we go. Let's zoom out. Let's watch this thing go. So if I hadn't had the surface, this is what would have been happening. Oh, that is really cool. I was not expecting that. So now let's let it fly here. This is that curve. Here it comes into screen. There it goes. That is an incredibly interesting example. Like that. Okay,
No.
what surface is it on? Well, that helps me visualize it. It's this surface. Let's make this surface come further out. Oh no, I know. I'm asking too much of you, computer. I need a better computer. I understand. Okay, this is this shape. At every moment in time, this thing is on this shape, which is pretty valuable for studying what's going on. So I just wanted to show that because I think that helps us understand why we're doing all this weird stuff. Because if you're going to study 3D motion, knowing the surface you're on is pretty valuable. There it goes. That's pretty cool. Yep. All right, let's leave that since my computer doesn't think it can handle this. That's this idea of surface of motion. All right. Apologies here. So can you still hear me? My computer didn't die there?
Yes.
Okay, good. So I forget what our answer was. If you did traces, oh, we could talk about that. But let's see, there's another question. Should we move on to something else? Ostrov 23, number 3, talks about curvature and normal component. Okay, lovely. Let's take a peek there. Okay, we're gonna look at Ostrov 23. Darn it. Don't have it at the ready. But I can find it. Ostrov 23. Number 3. This one. Curvature. Oh, it's one of these. He likes to have an occasional question on his test that is of the form, give me an example. And it gives you so much freedom, and you typically we don't want it. So I think that's what this sort of question is. For each of the following, give an example. Is that your question, Isha? Yep. A vector whose space curves intersects the plane twice. Oh, it's so free form. I don't, there's so many answers. I guess it's helpful to know that z equals 2 is this plane, everything that's 2 units up. We need something that hits it twice. Essentially, any parabola would do. Of course, there's many other things, but I only wanted to hit it twice. And so here's what I would do to stall for time, is I would write this. A line doesn't work, but almost any parabola would work. Yeah, I wonder how he expected, how he wants students to think through it. I mean, what I would do probably is something like just make it a 2D problem. How do I do that? I make y 0. And then I would draw a parabola that looks like this. That is tough though, because I'm using, my own knowledge to do that. But a parabola that would do this that goes above 2, how about 3 minus t squared and t? But that's kind of tough. A vector whose normal component. So I need to talk about some of these things maybe before we launch into this question. Um, and that's part of what this is good information because this is part of what I'll try to cover. I mean, I can give you a sneak peek of what I'm going to do in a moment, probably tonight or tomorrow, is I'm going to talk about how we think about curves, how we think about pyramid, these sorts of things as the intersection of two surfaces sometimes, how we find tangent lines, how we find unit tangents, how we do angle of intersection. That's what I'm going to do in a moment when I do that other video. And then I'll do another one that talks about the TNB frame in acceleration and curvature. So that might be stuff I have to cover elsewhere, but I think there's some interest. I will in the next 2 days do a couple short videos with examples from old exams on those things. I think of those as the starting places is knowing how to find the tangent vector and the tangent line. And then the next step is how do we measure curves in 3D? Measuring curves in 3D requires more tools. And this is the so-called TNB frame. So anyways, that's the stuff you're doing in chapter 13. It's not as exciting as the picture. It's all computational. Um, but maybe I don't know if I can quickly answer your question. I think I'm going to steal everyone's thunder for a second and make some executive decisions here. So here's a page. Let's do a little tour of how would you start? Let's play the how would you start game. And when we play this game, I want you to envision that you're sitting in your quiz section. The exam has been handed out. You showed up late. You're sweating. You didn't get much sleep last night. You just had an argument with your friend. You need a good grade. Put as much pressure on yourself now when it doesn't matter, and just ask yourself, what would you do? Now, there's a few different things going on here. So let's sort of look at the page for things that we would be able to do immediately without thinking. And then I'll skip the line and plane and then we'll do a curve, but just since we haven't done this yet. So to me, this would be a quick, somewhat no-brainer, the area of a parallelogram. That'd be something on my note sheet. So we'll come back to the other one in a second, but how would you do the area of a parallelogram? What would you be thinking? What are your first thoughts?
The
Cross
cross
product.
product.
Perfect, yeah. And they told you one of the sides, they told you this
Yeah, we had
side.
that last quarter too.
Yep. And so you would need to also find the other side, AB. So this is going to be a straight cross product game. AB would be 1, 1, 2, cross product, and then find the magnitude. What about the angle between the two? And I'm going out of order because I'm showing you that if you open the exam and you were scared of part A, just take a breath and look at part B, especially when it comes to vectors. We can come back to that in a second. We just can't let it derail us. Um, to this as a standard plan. So if I was somebody preparing for a test, I would be like, okay, this is money in the bank. I have this point B, I have this point A, I have this point D. I need this angle. That's what that means. And the most important thing about this question, and you encountered it in the homework, is you need two vectors that point out of A. Why do they have to point out of A? Because we would like to use this theorem. I call this a 10-star theorem. And when I do this in class, we put 10 stars around it and I jump up and down and point at it and do a bunch of arrows. And I say, we just can't forget this. But in order to use this, you have to realize your vectors have to be pointing tail to tail. And that's why it's so important you subtract in this order. And then you plug in and solve for theta. You're going to use that a whole bunch of times throughout the term. Every time it says find the angle of intersection, find the angle between two planes. I guess those are it. You are going to be using this. So those are fairly standard things, but how about C there? How would you do this? This is more of an understanding of vector question. It's more of a question I like to ask. You can't, sorry, I'm gonna say your name wrong, but Davia, I'm sorry. That particular, the identity for cross products has a sign in it, not a cosine. And there's two reasons I don't ever use that one. The two reasons I don't use this identity are the following. The first reason I don't use it is because I don't want to do a cross product. A dot product is easier. The second reason is because I don't want to work with sine. So there's a couple issues. Why don't I want to work with sine? Well, if you do inverse cosine, you'll always get an answer between 0 and 180 degrees or 0 and pi. Inverse sine gives you answers between negative 90 degrees and positive 90 degrees. So if you work with cosine, you don't ever get these negative angles. So there's a couple reasons I would prefer to use the first one, but the main one is just it's faster. Yeah. Okay. And then what about that point C? We can find the vector AB and then add. Yeah, so because it's a parallelogram, it's basically this idea. If you know the vector AB, which would be 1, 1, 2 by subtracting, then the vector C, I guess DC, is also that. And this is something I tend to ask, but it's also something I tend to emphasize in lecture. And what I really want students to be able to do is understand what a vector does. I like students to think about it as changes in this course. In other courses, a physics course, you might think of it differently, but I'd like you to think of as the changes to go from D to C. Okay, so let's sort of talk about that. And I feel like this gives a good idea about changing. I know the point here is 1, 2, 3. So if I walked from A to D, I know the changes. They're right here. The x coordinate is going to go up 3. This is going to be 4. The y coordinate is going to go down 1. So this is going to be 1. And the z coordinate is not going to change. Oh, this was not an optimal way to do this. That's probably what people are saying in the chat. Couldn't we have done it easier? Probably. Now I'm gonna walk from here to here. Do I know the changes? I do. 1, 1, 2. So 1, 1, 2. How did I do? I didn't check my work yet. But I usually ask some question, one small question about that because it gets to the heart of if we know a point and we know a vector from that point, we also know the other point. Okay, we already did the line and plane ones. They were kind of mean. And then we get to this question. So let's keep going a little bit because I want to, maybe I made a mistake by having being too open-ended, but consider this curve given in this terrible way. Find parametric equations for the tangent line to the curve and give the point of intersection. So this is one of these things. I mean, your instructor might not say the same. They might have different things to emphasize, but I tell students I will always ask about a tangent line because it's an important object. And so we just need to have a plan of attack. And when I look through exams from other instructors, most of them also ask this. So the moment you see tangent line, it's asking for a line. And so you would write X, Y, Z, blank, blank, plus, 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 T, 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 and you know you're trying to find a point and a direction. They told me the point. It goes through the point 3, 1, 8. So sort of no reason not to immediately do that whenever you're finding a line, and in particular a tangent line. Now for a tangent line, this should be a tangent vector. I tell students, if the word tangent appears in a problem, you're always going to do what? Probably going to do what? Take the derivative. Yeah, take the derivative. So anyways, so we need to take the derivative. R prime of t, and that just means component-wise derivative. Ooh, we get a little chain rule action. I just asked a derivative test in my business class, and this was hard for them, that particular one. So if you can do that, you're doing better than they are. So I need to take these derivatives. It's going to be 1/2 4t plus 1 to the negative 1/2 times 4. That's chain rule. E to the t squared minus 4 times 2t and 3t squared. Now, interestingly, what I remember from this exam is a lot of students did this and then they didn't know what to do next, which was an interesting. Yeah, I'll post the recording. I just need to think about how to share it with all of you. And I didn't think ahead of time to collect your emails, so I'll have to think about how that goes. Anyways, here's our function. I think I could just put a link on my website. I just don't know about posting on my YouTube. I have to think about that. I'm going to look at the recording. Some of your names would be on there. I don't like to post other students' names on YouTube in any way. Okay, so anyways, there's one problem here, which is what in the world do we plug in for t? And I can tell you what I remember is some students plugged in 3, some students plugged in 1, some students plugged in 8, some students plugged in 3 in the first one, and 1 in the second one, and 8 in the third one. Problem is none of those are t. So there's this little side thing that I remember when I asked this, I was surprised that this ended up being the stumbling block. Yeah, so we need to know what t is. Now they didn't tell me t, they told me x, y, and z. That's why I wrote this here. They told me x was 3, this was 1, and this was 8. So I need a t value that makes all 3 of those work. But you don't need to solve all 3, just solve one of them. But you're right to say that it's 2, but then you could check the other ones. Does that come out to be 1? Yes, because it's e to the 0. Does this come out to be 3? Yes. I had to pick numbers that worked. So you have to plug in 2. The other issue, which is not really a mistake, but I probably shouldn't have used the t here because I'm starting to get confused by it. I should have used something else because t was already taken. And I wouldn't mark someone off for using a t. Here it doesn't matter, but it's easy to get confused. If you start to do the intersection of two things, we know we need a different letter. So it's just good policy. If t is already in use something else as your parameter. Okay, so now I need to plug in a 2. So I think this is 12, 3 times 2 squared. I think this is 4 because it's e to the 0 times 4. And then this one is, I had a student tell me in business math that their instructors taught them the telephone method. It's an old style telephone. It's rearranging a multiplication. But that was funny. I'd never heard anybody call it the telephone method. So that's a new one for me. Anyways, we are going to simplify that, and I want to plug in 2. So that ends up being 2/3, I think, because the bottom is just 3. So that's how you find the equation of a tangent line, is you find the derivative, you plug in the t, but they already told you what it was, and you plug in the t to the other one. This is r of 2, and this is r prime of 2, if you want me to describe it in another way. I think I'll skip the intersection. The intersection part is actually fairly direct. You just substitute, 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 substitute. From that, you'll get u. This is another reason to use u, because I remember this exam that students used a t. They solved for t, and then they plugged that t up here because they forgot which one the t went with. So there's another reason to use a different letter. Cool there? So that's kind of 13.1, 13.2. And then we get into measurement tools, which is 13.3, 13.4. And that's going to be the rest of my exams. We could peek at a couple of those. Is this all right? I'm kind of dominating now, but we have an arc length question. We have a naming a surface question. So maybe let's zoom out and we'll finish with maybe a couple things. So we have arc length, name a surface, curvature, and throw an object at Dr. Lovelace. No, this is not at me. I'm just throwing an object. Oh, I usually have them throwing at me. So which one do we want? So you'll have to say 3B, 4A, 4B, 4C. Naming a surface. Yeah, that's a fast one. Yeah, whoever's the fastest wins. It's not actually a vote. I should have said that. Find and simplify an equation for the surface consisting of all points whose distance to the y-axis, oh no, it's 5 times the distance to the plane y equals 1, and give the names. This is mostly a naming problem. It's not something you have to visualize. It's a translation problem. So the main thing in these, when you're trying to describe all points, label those points x, y, z, and then try to write down what it says. So I'm going to write it in words first, and then we'll talk about it. So I want the distance from x, y, z to the y-axis to be equal to 5 times the distance from x, y, z to y equals 1. That's your job in such a problem. And I have a certain idea about how to approach these. And this is more about just thinking in terms of your coordinate plane. But the strategy, the first day of class, I actually do this. I do something similar. So I'm going to make all of you do this with me. So I grab a point out in 3D space. I usually pick a corner of the room and I pick a student and I label where they're sitting. And then I label the walls and the axes. And we play a little game in the room. And I say, it's very hard to draw depth in 3D, but I feel like I should have drawn that higher. Let's come up here. So this is 1, 3, 2, let's say. The questions I ask them, and we'll just ask you for a second. If you go straight down, how far is that to the ground? So the distance from 1, 3, 2 to the XY plane. And I have a certain thought process I always do. I don't try to use a formula. Just tell me the number. How far is it from 1, 3, 2? It's just 2. It's 2 down. But if you want a general strategy, you just find the corresponding point. And in order to be on the ground, z has to be 0. And in order to be directly below it, the other two numbers have to be the same. So basically, we were finding the distance from these 2 points. And you could have even used the distance formula. 1 minus 1 squared plus 3 minus 3 squared plus 2 minus 0 squared is 2. So if you can find the corresponding point, that's how you do these questions. Okay, so now let's say another one. Let's pretend I want to go to the y-axis now. Same point, 1, 3, 2, and I'm going to walk directly over to the y-axis, to the closest point on the y-axis. And I usually do that in the room. I'm like, if I walk from that student straight over to the y-axis, and I want to know what this distance is, what's the corresponding point? So if this is 1, 3, 2, and all you have to know is what does it mean to be on the y-axis? So what does it mean to be on the y-axis? What does that point look like? And the moment you start thinking this way, these problems become easier. So I just try to think, what is the corresponding point that is closest and on the y-axis? Well, in order to be on the y-axis, x has to be 0 and z has to be 0. In order for it to be closest, let's just talk about this point for a second. What do you think in this example the y would have to be closest to the point 1, 3, 2? It'd have to match up. So here's the jump. If I give you any point x, y, z, and I make you go to the closest point on the y-axis, this is just going to be the same y as this y. That's how I translate these problems. And after you've seen this, you can go, okay, y-axis, those are 0, closest point, same y. And then you can just use the distance formula. X minus 0 squared, I'm doing this minus this, plus y minus y squared, plus z minus 0 squared. And that's how I remember these. So this side over here is the square root of x squared plus z squared. And I just had to figure out the corresponding point that was closest. Now we're going to play the game again. And I'm going to go from x, y, z to the point that's on the plane y equals 1. Now that's, maybe if I did this in two, I don't know if I can draw that very well. Let's just talk about it briefly. So here's x, y, z. Y equals 1 is the plane that is 1 unit out on the y-axis. It's very similar to the xz plane. So let's talk about the xz plane first. If you were to walk straight over to the xz plane, then the coordinates for that would be, let's see, y would be 0, and x and z would be the same. That's the same idea here. It's just we're not going all the way over. We're starting from our point x, y, z. We're going to walk straight over until we hit this plane. What do I know about that plane? Y is 1. What do I know about x and z? If it's the closest, they're the same. So this is going to be x, 1, z. And you could start to see how these go. So you go, okay, I want the corresponding point that's closest, which means that whichever variable they're not telling you has to be the same. So that's how I remember how to do these. That's more of a 12-1 question, so that's why it's been a while. But now I would write x minus x squared, and then I would write y minus 1 squared. So this part really doesn't have to do with naming a surface yet. It was translating. So the first was saying, what's the distance from xyz to 0y0? And what's the distance from xyz to x1z? Yeah. I would not want to do this with the distance from a point to a plane. You'd have to get it in the form to match that formula. So don't think that's how I would do it. But let's finish it off now. No, what just happened? Let's see. Fixed. Here we go. Let's try to just erase this. Oh, there we go. There we go. There we go. Lovely. Okay. So if we clean this up, we have x squared plus z squared equals, sorry, the square root of this equals 5 times the square root of y minus 1 squared. I guess we need absolute values, but if I square both sides, I'm going to get x squared plus y squared is 25y minus 1 squared. What is that? So in this situation, we have all three are squared. And when all three are squared, typically what we like to do is get everything Oh, iPhone 105. Let's see if I can find the mute. Oh no, they took care of it. Shouldn't the second term be Z? It should be. I was seeing if you were paying attention. Um, since all three are squared, oh, it should be here as well. How about? And one of them's a minus. It's a hyperboloid of some flavor. There's a hyperboloid of one sheet, there's a hyperboloid of two sheets, and then there's a hyperboloid we don't call a hyperboloid. There are three of them. One sheet, two sheets, and a cone. The cone is like a degenerate hyperboloid. Um, anyways, so in this case, it's a zero on this side. When it's a zero on this side, it's a cone, circular cone. Boop, cone name goes here. If this were a positive number, what would you say? So if this were a 7, one sheet or two sheets? If it's a positive number, it's actually one sheet. Yeah. And if it's a negative number, it's two sheets. The way I don't remember it that way, what I do is this. If somebody gives me a number and puts it here, negative 14, what I do is I say, okay, if I were to do the traces, if you got rid of the x, it's a hyperbola. If you got rid of the z, it's a hyperbola. Hyperbola is always if you have a minus and you have two squareds. That's a hyperbola. And then the other trace is how you decide the name. So basically, here's what I do is I go, okay, this is a hyperboloid. And then I erase the other one. And I say, does that circle make sense? If that circle doesn't make sense, it's a hyperboloid of two sheets. If it does make sense, it's a hyperboloid of one sheet. And if it's an extremely small circle, it's a cone. That's it. That's how you figure out the name. So it's just a question of, are there circles for all values of the other number you have here? And here the circle when y is 0 is just 0. Here the circle when y is 0 actually exists. And it would be the square, the radius would be the square root of 10. And if you make this side negative, it doesn't make sense. So let's say you make this a negative 3. This doesn't make sense unless y is big enough to compensate. Meaning if y is 0, this doesn't make sense. But if y is, bigger than the square root of 3, it will make sense. And that's when you start to see circle. That's where that came from. That's why it has those special names. What time is it? 7:30. Okay, my other Zoom meeting's at 9. I was thinking it was about to start, so we'll see if anybody comes to that one. Tell your Math 124 students to come. I just felt like if I was going to do a 124 review, I should do 126 because I know so many of you. Curvature is a straight computation thing. In order to figure out curvature, you have to figure out R prime and R double prime. My one bit of advice for curvature problems is compute the derivatives first, and the moment you're done computing derivatives, then plug in your number. Because the formula itself for curvature goes something like, you'll have to remind me, it's the cross product of these two things. Is that right? All over. Now my brain is starting to be fried here. Let's go take a look. He didn't remember it. Let's go right here. I was thinking of another. So the curvature is this. Okay. R prime cubed. R prime cubed. So if I was doing this question, the first thing I would do is I'd compute the derivative. The Lovelace law of the C says if it starts with a C, it's a negative. Yeah, we'll do maybe after this example, go and do identifying surfaces one last time. So this is 2 cosine of t, this is 2at, and then you do it again, negative 2 cosine of t, negative 2 sine t, 2a. The moment you are done taking derivatives, that's when you can plug in your numbers. You can't do it before because if you plug in numbers right away, everything's a constant. You do not want to do the cross product of these two things unless the question asks you to. And the question does not ask me to. It just asks me what happens if I plug in 0. So now is when you would plug in 0. So this is an important little observation of efficiency. 2, 0. R double prime at 0 is -2, 0, 2a. Now you do the cross product. When do you mean for maybe the other piece you were talking about, but so yeah, I think I'll sort of wind down here, but answer these couple remaining questions. The magnitude of R prime cubed. Yes, thank you. So I didn't have to look it up. So yeah, so we've hit a few things, but let's see if I can find something about naming surfaces. Let's look here. Somebody's asking about, Alex is asking about naming 3D shapes. So a good place to go would be here. I'm not sure that this is what you were asking about, but you can clarify in a second. So I have these quick notes, which is, unfortunately, you first have to know some 2D stuff. If everything's to the first power, it's a line. If one of the things is squared, it's a parabola. If they're both squared and there's a plus between them, it's an ellipse or a circle. And if they're both squared and there's a minus between them, it's hyperbola. That's the starting place we have to know in order to be able to name. So then we say, what are the names? So first there's a cylinder. So for everybody on here, how do you know if it's a cylinder? You can immediately tell if something in 3D is a cylinder. And unfortunately, the naming is weird. There's only 2 variables. That's it. So if there's only 2 variables, which is happening here, then you draw it in 2D and you extend it. So here, this just means draw a circle in 2D and then let Z be anything you want. It's like you're stacking up circles. We call it a circular cylinder. Here you would draw the cosine wave in the XZ plane and extend it out. Those are cylinders. So cylinder is the first name that's easy to identify. Let's keep going. So what if 2 of the things are squared? And I have 2 examples here, this one and this one. If 2 are squared and you do traces, let's play the game. Let's play the thumb game. If we cover up X, pretend that it isn't there, it's a parabola. Z equals Y squared. So parabola. If you cover up Y, parabola. The moment you see that 2 of the traces, the X trace and the Y trace, are parabolas, that tells you it's a paraboloid. And then you go to the other trace to figure out what the name is. So if you cover up Z, it's an ellipse. So we say elliptical paraboloid. What about this one? So this one, when you cover up X, it's a parabola. It's a sad parabola. If you cover up Z, it's a happy parabola. That's this parabola going up, the parabola going down. If you cover up Y, it's a hyperbola, and that's what it looks like from above. This is called a Pringles chip, also known as a hyperbolic paraboloid. But it looks like a Pringles chip, and this isn't a very good rendering of it, but that's how you name it. Okay, so then you're down to the cases where all three variables are squared, and there's 4 of them. There's the case where all 3 are squared and there's a and everything's a plus, in which case it's an ellipsoid. And then there's a case when all 3 of them are squared and there's a minus. And all 3 of those I think of hyperboloids. And it just depends on whether the other side is a positive number, hyperboloid of 1 sheet, negative number, hyperboloid of 2 sheets, or 0. You could just put it on your note sheet, absolutely. But when I look at these, if someone gives me these, it's just we need these before we can move on. But when I look at these, I go, here's how I do it. I cover this up, I say hyperbola. I cover this up, I say parabola. I cover this up, I say parabola. 2 of the traces were parabolas, It's a paraboloid, hyperbolic paraboloid. This one I would say elliptical cylinder. This one I would say, oops, it doesn't make sense when I plug in a 0 for x. When I plug in a 0 for y, I get hyperbola. When I plug in a 0 for z, I get hyperbola. So it's hyperboloid that doesn't make sense. This idea of thinking about traces, which means hyperboloid of two sheets, this idea of thinking about traces will reappear in chapter 14, so it's good to have thought about it a little bit. This is such a small part of the exam, though. It's not worth a ton of study. Yes, you can put it on your note sheet. I just wanted to give a little bit of a reason where the names are coming from because that makes it easier to remember. All right, I think I'm going to leave that then. And Lily was asking about, you should ask your professor what to study. The number one studying resource for everyone is the homework. So I always tell students that. You should be going through the homework. And then beyond that, you should use any of the old exams in the archive for practice. Um, okay, you were talking about when do we use the square. That's more if you're trying to describe a curve. See if I can find such a thing. Maybe here. No, we already talked about that one. Maybe here. Thank you. Thanks for coming. We'll wrap things up here. Ah, that's not it. Yeah, I may cut it at that. Great. Glad it's helping you. I think I'll cut it at that. Oh yeah, if you're a former student, I guess I could message you about that. I'll post it on my, I'll see, recording usually takes a few hours to process and then I get a link. I'll put that link on my page here. I'll put it underneath this. Um, I guess it still is public if I do that, but it's not as public as the YouTube channel. So I'll put a link under here that says link to recording. All right. Good luck. Hopefully I see some of you around. I don't know that I'll do this for each exam, but I kind of was thinking I would do a little bit of each of the courses. Maybe I'll do a 125 one for the next exam, maybe a 125 and a 126, and then maybe, I don't know. It will always depend on my schedule. But I thought when I can do it, this gives me a little more insight into what resources I could make. I would like if you go on the YouTube channel, to add comments where you have ideas of things I could add or things that were helpful. Um, because I am trying to build this into a little more helpful resource. So a little bit of feedback on there. And also just check out my goofy other videos, sports videos, just for fun. This is more fun than studying. Check out this one. I got all sorts of things here. Oh boy. If you really want to see why the rationals are uncountable, this is what I really want to do as students that learn about some other things. How the roots of unity saved my dad's life, why calculus students don't like pancakes, or don't like donuts, how to cut up pancakes. I got a lot of stuff here. That's more fun. Lately, I've been throwing tennis balls at the statues around UW campus to measure how high they are. I've measured a lot of statues. Uh, where else are the other ones? I did spirographs. I made an animation of the Disneyland teacups. I got a lot of stuff there. Check it out. Okay. Take care, everybody. Recording for this I'll post on my website. Yep. Lovely. Now I just got to figure out how to turn it off. Stop sharing and end.